In this video, we're going to talk about how intermolecular forces influence some properties of liquids. The first property that we're going to talk about is surface tension. Surface tension arises from the fact that molecules in the interior of a liquid are more stabilized than molecules on the surface of the liquid. And that's because molecules on the interior have more molecules that they can interact with through their intermolecular forces and are therefore stabilized, whereas molecules on the surface have less of those intermolecular forces attractions, and so they're less stable. As a result, liquids tend to try to minimize their surface area, and this gives rise to what we call surface tension. So one manifestation of that is water beating up on some surfaces. A sphere has the minimum amount of surface area, and so water droplets beat up when they're trying to minimize their surface area. And something with stronger intermolecular forces will hold that shape better, whereas things that have weaker intermolecular forces sort of succumb to gravity. Surface tension also results in sort of a film developing on the surface of liquids. And the stronger the intermolecular forces in the liquid, the stronger that film is. And water, having strong hydrogen bonding, has extremely strong intermolecular forces, and so it has relatively high surface tension. And so, bugs that are able to walk on the surface of water, even though they're more dense than water, and so we might expect them to sink, they're taking advantage of this surface tension film on top of the water to not fall into it. Another property that we can relate to intermolecular forces is viscosity. So the viscosity of a fluid is the ease with which that fluid flows. And so an example of something that's more viscous is something like maple syrup, right? It's sort of really thick and it flows very slowly. That would be something with a high viscosity. And so the more the molecules want to stick together, the higher the viscosity is going to be. And so as a couple examples, we have a list of hydrocarbons here. Right, so hydrocarbons, these all contain only carbons and hydrogens, as you can see based on their formulas. And so all of these compounds only have London dispersion forces, but as the molar mass increases and the chain of these hydrocarbons gets longer, we would expect their London dispersion forces to get stronger. And so as we go down this list, we would expect intermolecular forces to increase. And we can also see the increase in the molar mass. And so you can also see what happens to the viscosity. Right, as the size of the molecule increases, the strength of the London dispersion forces increases, and these liquids become more viscous. Now, intermolecular forces aren't the only thing that influences viscosity. Temperature also plays a role. If you think about taking maple syrup or pancake syrup out of your fridge, right, it flows much less easily than if you heat that up. And that's consistent among different liquids. We can see this is the viscosity of water at several different temperatures, and you can see as you heat the water up, the viscosity decreases. All right, another property of liquids heavily influenced by intermolecular forces is vaporization, the conversion of a liquid into its gas state. And so we often think of this with boiling, but a liquid doesn't have to be at its normal boiling point in order to evaporate. If you think about setting a cup of water outside on a hot day, that water is never going to reach the boiling point of water, but it will evaporate over time. And so what has to happen for a sample to evaporate, or for a molecule to go from the gas phase to the liquid phase, is that it has to get enough energy. Has to have enough thermal energy so that the molecules can escape the intermolecular forces that has in the liquid and then get ripped off when it goes into the gas phase, and it doesn't get those intermolecular forces anymore, because in the gas phase the molecules are too far apart. And so what we're seeing here is on the x-axis we have the kinetic energy of our sample. We have the fraction of molecules that have different energies. And as we saw last semester with gases, temperature is a measure of the average kinetic energy of a sample, but molecules within that sample can have, and do have, a distribution of energies. And so if this dashed line is the energy needed that a molecule has to have for it to escape the liquid and turn into the gas phase, then we have two different temperatures of the sample here, the blue at a lower temperature, the red at a higher temperature. And we can see when we look at the red curve and the blue curve, the fraction of molecules that have enough energy to escape the intermolecular forces and go into the gas phase is higher, as we would expect for the sample at a higher temperature than at the lower temperature. And so there are a number of factors that influence the rate of vaporization. Certainly temperature is one of them. If you heat the sample up, more molecules will have the required energy and they'll be able to escape the liquid and move into the gas phase. Surface area also plays an important role. If you have a water molecule down here in the bottom of the beaker, even though it might have enough energy to escape and go into the gas phase, it can't get out, right? It's going to bump into all these other molecules, say on its way to the surface, and it's going to lose that energy. But the greater surface area we have, the larger percentage of molecules that find themselves with enough energy and are close to the surface and are therefore able to evaporate. And then, of course, intermolecular forces also play an important role, right? The stronger the intermolecular forces are, the harder it is going to be for those molecules to escape, and so the rate of vaporization is going to be slower. Now, closely related to vaporization is the idea of vapor pressure. So, if we take some water and put it in a flask and put a stopper on, at least initially, there's not going to be very many water molecules in the gas phase. But over time, some molecules will acquire enough energy to get out of the liquid phase and move into the gas phase, even if we're below the boiling point. But then also, if they happen to recollide with the surface of the liquid, they can lose some of their energy and they'll go back into the liquid phase. And so we constantly have new molecules going into the gas phase and molecules that were already in the gas phase going back into the liquid phase. And at some point, once things stabilize, we'll end up with a steady concentration, or the pressure of water molecules in the gas phase will stop changing. And we'll reach a situation called dynamic equilibrium, where the rate of the molecules going from the liquid phase into the gas phase is the same as the rate of molecules already in the gas phase going back into the liquid phase. And so the pressure of the gas stops changing because the concentration stops changing, but we call it dynamic equilibrium because at the microscopic level, things keep changing. New molecules go into the gas phase, molecules are already in the gas phase go back into the liquid phase, but because these processes are happening at the same rate, we've reached a state that we call equilibrium, where in the macroscopic sense, we don't observe a change in the pressure. And so we can sort of see what's happening, at least initially. The rate of evaporation doesn't really change. The surface area is sort of the same, and so the rate that the molecules are coming off of the liquid stays constant. At least initially, there are no molecules in the gas phase, so the rate of condensation is zero, but over time, as we build up a concentration of molecules in the gas phase, they start recondensing. And then once these two rates become equal, we've achieved our dynamic equilibrium. And so vapor pressure of a liquid is what is the pressure of the gas above a liquid in a sealed container. And so this depends on the substance. Substances with stronger intermolecular forces, it's harder for the molecules to get in the gas phase and they'll have lower vapor pressures. Things that are very volatile, that have weak intermolecular forces, it's easier for the molecules to get in the gas phase and they'll have a higher vapor pressure. Of course, this also depends on the temperature. If you increase the temperature, the vapor pressure will also increase. Okay, so let's look at an example. So I want to know which of the following compounds would have the greater vapor pressure at 25 degrees Celsius. And so we have to consider the intermolecular forces. Which one of these compounds has stronger intermolecular forces? So we have water. We know what water looks like. And we know that water is able to undergo hydrogen bonding. Dimethyl ether we've encountered before. right? Dimethyl ether has polar bonds, and it's asymmetric, so it's polar. So it at least has dipole interactions. But because none of the hydrogens are directly covalently bonded to the oxygen, it can't undergo hydrogen bonding. So we've got hydrogen bonding in water, and we have dipole-dipole interactions in dimethyl ether. And so certainly water should have a higher vapor pressure than dimethyl ether, assuming they're at the same temperature. I'm sorry, that's backwards, right? Water has the stronger intermolecular forces, so it'll have the lower vapor pressure. Right, in dimethyl ether, having dipole-dipole interactions, weaker intermolecular forces, it should have the higher vapor pressure. Right, and if we consider ethanol or ethyl alcohol, we have polar bonds. It's asymmetric. In this case, we do have a hydrogen directly connected to an oxygen, so it will also undergo hydrogen bonding. And so of these three compounds, the one with the weakest intermolecular forces is dimethyl ether, and so it should have the highest vapor pressure. Okay, one more topic related to this, and that numbering is wrong. We're in chapter 10. But let's talk about boiling point. So normally we say, like if I were to ask you what is the boiling point of water, hopefully you would tell me 100 degrees Celsius. But we have to be a little bit careful. The definition of boiling point is that it is the temperature at which the vapor pressure of the sample equals the external or atmospheric pressure. But we know that atmospheric pressure is not a constant. And so as atmospheric pressure changes, or as atmospheric external pressure changes, the boiling point will actually change. So when we say that the boiling point of water is 100 degrees Celsius, what we're really saying is what is the normal boiling point of water. So the definition of the normal boiling point is the temperature at which the vapor pressure equals 1 atmosphere, right? So when we've specified 1 atmosphere of pressure, then water boils at 100 degrees Celsius. But if the external pressure changes, either we put it in a vacuum, so if we put water in a vacuum and suck a lot of the air out to lower the pressure, that water is going to boil at a lower temperature. Or in sort of practical cooking terms, if you live at higher elevations, atmospheric pressure is lower. There's just less air. And so you may notice, like on cakes and brownies that you buy at the grocery store, like the packaged stuff, it'll often have, you'll see sometimes it has high elevation directions. And that's because if you live in Denver, Colorado, or somewhere else that has a high elevation, the atmospheric pressure is lower, and so water actually boils at a lower enough temperature than at lower elevations, that you have to take that into account when you're cooking things. And I have another video with some additional examples where you're given some molecules and you have to decide which one's going to have a higher boiling point, higher vapor pressure, higher surface tension, or what have you.